Great. Yes, I will talk to you about generative systems design. The question behind this is, can AI build machines? So I'm going to do this in several stages and also basically split up the question in some sub-questions and try to give some answers or at least hints. Um, some parts of the presentation are based on the work from Michelle Zinsberg and Michael Rudloff, so I didn't name them explicitly, but I will say where their work is inside. And other parts of the work are inspiration that I took. If you look at the engineering process, most of you know that. The engineering process is always a cycle. It has some back loops, but first you want to identify what you want to do. So you ask a question, you ask, how can I solve this? Then you find out more about this problem, you research the problem. Then if you're creative, you imagine some possible solutions to this problem. And then, of course, you have to try them out. So you plan the solution, you choose the most promising solution, you create it, you make a first prototype. Might it be hardware or software, doesn't really matter, but you create a first prototype. Then you will test this prototype, see if it actually works, how you thought it would work, and evaluate that test results. And if they are not good enough, you will improve on your idea. So you always have this cycle. And some of these steps might benefit from AI. So my idea, or the thing that I want to present to you today, is if in this imagine step and also in the research step, AI might help to give you more ideas, to give you a wider range of possible solutions to your problem. You can split it up in two design questions. One design question on the left-hand side is you want to design a system, which is typically if you want to build a machine. And so the input that you have is the set of components, let's say the Festo portfolio. You have the environment in which the machine should work in the end. So is it wet? Is there does it have to be food-proof? Stuff like that. You have some requirements for the machine. And then you have a task, of course, that you want to solve. So let's say you want to produce a pneumatic cylinder. So that is a pretty clear task. In the beginning, you have some aluminum and some other materials, and in the end, hopefully, you have a pneumatic cylinder. And then you want to design a system that does exactly this. And the other side of the problem might be maybe you don't have all the components that you need. Maybe there are some components that you still want to design or that are still needed to solve the problem that are not there in the portfolio or wherever you look at, and then you want to design new components. So the input there would be the requirement for the component. How big is it? How much force does it need to have? Also, does it need to be a clean design? Can you use oils, stuff like that? And those are the requirements, and then also the environment. So in what size can I build it in, stuff like that. And then if you have the system and the component, of course, what you also need is the inner part. For the system, you need to program the system. You need to have typically a PLC controller that tells the system what to do. We saw this yesterday in the keynote of Mr. Krivet. He also said, typically you just buy the gripper or something that moves, but you need a valve and you also need a controller that controls that valve. So you need somehow to tell the system what to do. So you need to program it. And on the other side, if you have components, you need to control the components. So this is what all the control engineering is doing. A component on its own cannot really move in a good way. So you have to have a very thorough control algorithm for this component. And now in this talk, I want to go through both of these and share some ideas that I have about how can we use AI or generative models to support some of these steps. Let's first look at the design of systems, which is, to my understanding or how I see it, a bit easier because you already have the components and the components already work. So you already have the building steps to build your system, but it's still highly challenging. So the input are, as I said, component, environment, and the task, and the output would be a system. And if you want to program the system, the input is the system and the task. So what does the system need to do and what kind of system do you have? And the output might be a task sequence. So that's like very abstract layer. Of course, there are a lot more things to it, but let's say that's like the basis. And now the first question that I want to go into is, what if a machine could know how to solve a task. So you have a machine, you have a system of machines, and it somehow miraculously know what steps it needs to take to solve this task it has before itself. So the basic idea here is that if you have two states, you have the initial state, the machine is there and it has some raw materials, or it has an environment and has some stuff in this environment. And you have a goal state, which is, let's say, the desired product is produced. And in between, of course, you have a transition between those two states. So what you want to have is you want to find this transition T in a way that it actually leads from the initial state to the goal state. This is a very typical planning problem. So typically, one approach that you could take is a backward search. You start from the goal state, and then you search possible states that lead to the goal stage, and you repeat that process until you are in the initial state. There are other methods to do this, but let's just stick for this for better understanding. So as you see, you split it up in different tasks. You start, and then you always have, in this first step, you have a T1, which will be the first iteration. You come to a certain point, and you still need to solve the T1 until you, at some point, reach the initial state. And that is exactly this control or the task sequence that you need. So in this example, and this is work that Michael did, as I said, in this example, we have a system, a predefined system. It contains a fixed block and a moving block, an axis and a gripper. And it has to solve a task that is visually defined. So the task is defined by move the balls, like the filled circles, into the empty circles of according color. So very easy task. And system is given. So what you can do here is have a planning algorithm, for example, any kind of planning algorithm, let it be A star or some other planning algorithm. And then you can give it even some boundaries, run an optimization over it, and find an optimal task sequence that will solve this sequence or this task for you, if it's possible. So A star, for example, will always find one if there is one. And this is the output. So you see that this predefined machine found a way in this discretized space. It is very much simplified. It's a 2D space and discretized, but it found a way to solve this task with as few steps as possible. That was the optimization, as far as I remember. You could also think of something else, another optimization, but that is one option. And then the output that you get is this task sequence, right? So you say move to a certain space, then pick up, then move to another space in this 2D space, then undo the pick, so let it go, and move, and so on. So you have a sequence of tasks that will solve you this problem, and you found them by planning. This might look a bit more complicated, so you could have a whole tree where it's not just sequential, but you have decisions to take. You have to have a sensor, for example, and only if the sensor is true, you go to the next state. Otherwise, you wait. Stuff like that might be in there, and typically it is much more complicated than what I just showed. But I just want to give you indication. So if you have this sequence of tasks, then what you can then do, and that is what we saw yesterday also in Dieter's keynote, so I'm referencing a lot of this work, you can give it to a machine. Let's say it's a very universal machine like a robot. And if you give this robot this task sequence, it will be able to move on it, right? So you have a kind of decision tree where you can dynamically move on this decision tree. You can solve the task, and if something is in your way, you can go back and try to resolve it. So how this looks like is this. The task is make this tower, and these are two iterations of the same robot doing the same thing, but we perturbate the environment a bit different. So as you see, there is an interaction with the environment. We move away blocks and annoy the robot a bit. And the robot dynamically reacts to it. So behind it is a hardly scripted task tree that we just saw. So that the tree itself doesn't change. It just knows what kind of sequence of tasks it needs to do and what decisions it can take. But it can move on this tree automatically. So if you combined it with what I just said, you learned this tree maybe, you found some planning algorithm to find the sequence of tasks, then actually I think it is possible to, in a certain environment, to have a machine that would recognize what to do. It would recognize what kind of tasks it can do, what kind of tools it has, and what it needs to do to solve a given task. At some point, you also saw when you remove, for example, this blue block, the robot will realize it has to unbuild the tower to rebuild it, because in the sequence of the goal state, the blue block is the furthest down. So yes, you will get an adaptive behavior, and this is definitely a first step into solving tasks or having a machine that knows how to solve a task. So from my current standpoint, would say this programming of systems AI can help you very well. So you have to validate it, and it's not the typical generative design AI that you know. You have to validate. You probably need to go to symbolic AI for it. But I think here you can really have a great help. And now let's go one step further. So if we go a bit more abstract and say we don't only want to program the machine, but we want to find the machine. We have components, but we want to find how to couple these components together. So the next question is, what if an AI could build a machine that then solves the task? So you just know the task, you want to build a machine and solve the task. And this now is a master thesis of Maike Rudlaff. She's not with us anymore, but was her thesis, so I want to still give her credit. Michael supervised it. The idea here is that you have a certain set of subcomponents that you can build a system of. So the components are a gripper, a cube, which is like a joint. You can connect some kind of axes. You have an axis and you have a block. Then you have a treatment option to paint something, like a brush that paints a certain color. And you have a welding option that will join two balls together. So this is like the basic vocabulary that you would have to build this machine. Again, very simplified, but just to show that it in theory works. And then the machine itself is represented as a tree or as a composition of several trees. So you know how things are connected, how they interact with each other, and so on. So you have a logical representation of the machine as a tree. And in this first research, we gave the machine some more, but here are 3 example tasks that are to be solved. The first task is this. So the solution obviously is you have to paint one of these balls red and one green and then move them to their circle. For the second task, you need to weld those 2 balls together and then move them, or the other way around. You could move each of the balls and then weld them together. And in this last step, you have to paint, weld, and move. So we tried to show a bit of a complexity or increasing complexity of tasks. And the solutions you can see right here, I have to say, and Michael is always upset about it, there is no collision detection in this model. So basically you see a 3D space from top. That's the idea. But this is what the algorithm came up with. So it built these machines out of the components that it had. It moves the objects out and paints them. Here you see it's very efficient. It basically has 2 grippers and 2 painters. So it picks it up, moves it out, and paints. So there was no restriction on how many components you should use. But you could do that, for example. You can say only use as few as possible components, and then you would get as small as possible machine that then obviously needs some more steps to solve the task, but it's a more complex machine. And how this was done is basically a twofold approach. In the inner approach you already saw in this first part of the presentation is a planning algorithm, and around this was an evolutionary algorithm that tried a lot of different solutions and iterated them. If one solution was better, it made like a child of those solutions. So I also really like this work. It shows for me that it is possible, if you just have a task and a set of components, that you can build a component and then solve the task efficiently. But of course, there are some challenges to this. So if we look in this first thing that I presented, programming of the system, there are the challenges that, as I said, the example that I showed was very much simplified. It was very discretized, and we would need to move to a continuous solution space to actually have meaningful solutions. The second thing is that you need, for all the systems that you have, you need some kind of digital representation. So you have to be able to try out some of the solutions that you make in a digital space in order to then move it to the real space. And the third challenge is that the capability of the system and what effect this capability has on the component. So like I have a gripper and I can grasp a component, but what does it mean for the component? It is fixed after grasping, and then you can move it around. So this interconnection of tasks and components needs to be somehow modeled. And at least I think one approach that could be taken here is reinforcement learning. So that is a promising space because it can handle continuous solution spaces, and it can also handle high-dimensional problems. So that might be one direction to tackle this problem of programming the systems. Another direction might be more complex planning algorithms or planning methods for continuous solutions, also possible. Also, in the design of the system, there are, of course, a lot of challenges still. The components have to be digitally described, including their behavior. So each component has to have a digital model also and know what it can do. But this is not enough. If you have this, you also have to know how these components can be connected. So how do they fit together? What screws fit in the other component? How can I connect them to actually build a real system? Otherwise, it wouldn't work. And it has to be clear how the single skill of a component translates to a higher level skill. Let's say an axis, for example, can move linearly, but it cannot do it without a motor and without a controller. So you have to somehow know this, because otherwise you will just put an axis there and then you would be confused that it doesn't work. So this has to be also modeled and has to be clear how to get from individual skills to capabilities. And I think here we probably should stick to a more symbolic AI like semantic web technologies that can model this kind of behavior and can also reason about things. It can reason what do you need to build something, and it's rule-based, so you can actually build a rule-based system. Okay, so far so good. So now we looked at this left side of the slides, and I would say there is a path forward, right? It's not solved, obviously. There is a lot of challenges still, but there is a path forward. And now I want to look into this right part. Can we have an AI that can develop components that we then use in a machine that then solves the task? So one step further, can we have this? And this, from my point of view, is also very, very challenging. If you look at a very simple component, it has so many little parts, right? So if you just unscrew a cylinder, you have so many screws and fittings and rubber bands and stuff like this. So you have so many things that you have to think about. So it might be very challenging. But let's see what we can do. So this highly goes into this area of imagine. You already know what you want to do. You research your problem and you want to imagine a solution. What can you do there? And the basis premise is that if you look at most of the components, or till some years ago, all of the tools that humanity had, they were all passive. It means that a human is in front of it and has to give it instructions, and then the tool does something. But the tool doesn't create anything. And that changed in some way for the modeling of mechanical parts, for example. We have generative design, which is a method where you give some restrictions. Like here, you're designing a drone body and you give some fixed points. You know, for example, where the propellers should be, where the motor is, how much force it needs to hold. And then you can have a generative assistant that tries out a lot of materials and a lot of forces and then just spreads over all of this design space. That's already known and already exists. You can have it in Creo or in Fusion 360. So there are already a lot of tools that already do this for hard and rigid bodies. But you still need to give the basic constraints around it. So you need to say here and here you have this force, here and here you have the propeller, here you have the motor and stuff like this. And then in this design space, you can design a rigid body that withholds all of these forces. But what if you want to be a bit more creative? If you just want to say, I want to have a pneumatic cylinder, and then you want to have a solution for that. And obviously, this is where the talk goes more into generative models. So if you look at these prompts, probably all of you know what is coming. If you see, I want to have an armchair that looks like an orange, or a drone that carries a package. So I describe the task on a very high and very abstract level. I just say I want to have something that does something, or that looks like something. Then I can use generative models and get something. And these are not very good, obviously. So nobody would ever buy any of those chairs. Or I don't know, maybe a museum would, but those chairs are not very good. And also the drones are barely recognizable. But the interesting thing about this is this is February 22. So it was a bit more than a year ago. And if you jump 6 months in the future, it already looks like this. So the step forward that we took in terms of quality of the image and quality what you get out of it in just 6 months is breathtaking, I think. So this is a DALL-E. Pardon? Looks like a chair, and it is orange. It doesn't look like a. Yeah, exactly. But it was done by just me putting this quote in it, right? So it's not really a design chair, but you could fine tune. Of course, you could say it should look a bit more like an orange, or it should have orange peel and stuff. I just gave it this very simple, input, and also the drone. I mean, it looks like a drone that carries a package. And then, of course, I tried it out and asked, give me a pneumatic cylinder. And that's what I got. So also it looks kind of like a pneumatic cylinder. I mean, it wouldn't work. I know it wouldn't work, but it kind of looks like it. Especially the first one at least has like an input nozzle and the output nozzle, and it looks like a pneumatic cylinder. And then I went one step further and asked it, give me a machine that builds a car. And well, here it goes a bit off the rails, but you can kind of imagine still a machine that builds a car. So it's not really helpful. And of course, all of these are just 2D images, right? So I mean, it's cool and impressive, and it looks all very nice. And probably all of you thought like, okay, cool. But it's still 2D images, so they don't work. There is no model behind it. There is no programming. You don't know if the system does anything. So how do we get out of this 2D world into, let's say first step, at least the 3D world? So at least I want to have a 3D model of what I want to have, and not just a 2D model. And there are already very well-known methods. You can use a lot of 2D images from different perspectives, and then you can use photogrammetry and generate a 3D model. So what it would look like is you have this set of pictures of a car, for example, give all of them to the photogrammetry, and give a 3D model. But these are all not pictures of a car that are taken. They are already generated by another generative model. So a style gun actually generated all of these with one input image. I think this one. The input image, the first, or this, I don't know, one of those two is the input image, and all the others are generated. So basically what you can have is an algorithm that just takes one image and imagines the rest. And then you can use that to put it into photogrammetry and create a 3D model. But why do this extra step, right? Why would I first imagine a lot of different pictures to just then put it into photogrammetry and then have a 3D model? Why not just do it directly? Give it one 2D image and then get a model out of it. And that also works. So that's another model, Gunverse 3D. All of these models are generated from only one image input, and you generate a 3D model of the whole car or bird. Yeah, it's not, especially the birds, not really awesome models, but it works, right? So you give it just one image, and you have a 3D model, and if it knows a bit about the object that is on it, like a car, it actually can create you a 3D model. So we are one step closer to maybe finding a solution to generating components. But again, just simple 3D meshes, actually. It's not even models. It was just a mesh of something. It doesn't have any moving parts, and as I said, very simple models. The car is basically a cube with with a little bit of other shapes. So it's a very simple model. But you can also generate a lot more complex models. So here, Get3D is another model that generates variations of the same model. So you give it one model, or you start with one chair, and then all of these variations are generated by the AI. So you get a lot of different types of the same instance of object. And why would you need that? Well, this is definitely to populate a virtual environment. So if you want to have, let's say, autonomous driving, you have a car in a virtual environment, then you need people walking in this virtual environment, and you need other cars driving in it, you need houses, you need all of these 3D models, and you don't want to have thousands of people creating 3D models for you. So what they do is you have a model that just varies over the solution space and gives you all of these different outputs. And then all of a sudden you can have a giraffe crossing the street in front of you. Might not happen very often, but it might happen, right? So you can do that. But again, meshes, right? So nothing here is moving. They are more complex models. They look very fine and detailed. It's really, really fascinating, but they don't move yet. They are just meshes. But also for this, obviously, as I bring up the question, I also show a first solution. So this is one of these generated models that you saw. And what you can do here is give it to another model, and it generates some moving parts, right? So this is the input image, and the output image is this moving 3D model. So you get out of one image, you get a driving 3D car. Granted, cars are not that complicated. You need 4 moving wheels and some lights. I see that, but it's again a step in an interesting direction where you can actually generate a fully working 3D model that can drive around in a virtual environment. Okay, so these are just some hints, some ideas in this direction, and as a light note in the middle, I want to bring up some other pictures that I generated that are interesting. But the interesting thing here is it's not actually a picture, it's a video. So you also have an input, just this one input, and then you get a video. And again, there are some weird things like here the legs of the elephant cross weirdly and stuff like that. But what you see here is that there is, especially in this teddy bear that washes dishes, there is some interactions of different materials, right? So there is some water in there. There are some the fur of the teddy bear, and there is the dish that he's washing, and you see some kind of interaction. And it is not perfect, but it is one step further from a generated 2D image, right? You have at least the video, you could have some logic behind it. And in this case, it's not done very complex. So you just limit the model that generates the 2D images, and then you know that they are not too different, right? So you generate a lot of images that are not too different, and then you make a video out of them. But still, another step in an interesting direction, right? And now another question. What we saw was a lot of interesting directions, but as I said, these different materials, if you design a component, you need a lot of different materials. You have aluminum, you have plastics, you have moving parts, you have like a lot of different things, and you need all of them in one part. And there, also one thing that I want to show you is NVIDIA Canvas. I was very creative, my old paint skills, and I painted this. I actually made it for a talk at the Tage des Systems Engineerings, which is TDSE. So that's why I painted that. So yeah, very creative. Painted this and said this there. Up there is a cloud, and here's a river, and then this should be wood and grass. All of you probably imagine it. But then what you get is this, right? So what you get out of it is just you can define where what material should be, and then you get again a generative model that creates you something like this. And if you say, okay, I mean, I'm not completely happy with it. Maybe these tree trunks should stand in a bed of sand. I don't know. Then you change this very bad input image and just say there is some sand under here, and then you get this. Right? So now you have some trees or some wooden parts standing in a bed of sand in front of a river in some grasslands. And then you click another button and say, I want to see different styles of that. And then you actually get different styles of it. Right? So you have different types of wood, different type of vegetation. The sand slightly changes, the lighting changes. So you get a lot of variations of this thing where you just defined the basic outline. So what you just did is I defined here is some material, here's some material, and they should be together. And then you get this output. And now you might say, okay, this probably takes forever, right? So if I do this, it's not very performant, but no, it isn't. So I will show you a live video here of how I did this. This is the tool, also Canvas, and you see on the left-hand side how I paint. Again, amazing painting skills. But on the right-hand side, you see right away how the image is created. And something like this could be something that a designer or someone who creates a component could use, right? It could have a very simple design interface where you design the basic tool or the basic component. And on the right-hand side, you get generated options of it, or you get a more defined option of it. So you just don't have to go through all the hassle in making it better, making it more nice, adding other materials. So that, again, might be some interesting direction to look at. And of course, I couldn't have a talk about generative models without talking about ChatGPT. So I have to bring this up. I just made this yesterday. And I was curious. I just asked it, what do I need to build a machine that produces a pneumatic cylinder? Exactly the question that I asked all of you in the beginning of the talk. What do I need for that? And it is actually pretty reasonable. It says it is very complex to have a system that designs you different components. You need to design the machine, you need the materials to do it, you need to assemble it, program it, test and calibrate it. So those are more like the basic steps how to design a machine, this engineering process that you saw in the beginning, right? So it just gives you the engineering process, and it says it can be very complex and involves a lot of specialized knowledge. But then I asked it, well, design a machine for me. Why not? Can you design this machine for me? And then again, it says that's a very complex process. I can probably not do it right away, but these are the basic components that you need to build such a machine. So you would need a power source, you need a material feeding system, you need a cylinder forming and cutting system, you need a surface finishing inspection system, testing and calibration, and safety feature system. So it breaks down the task of building a machine into subtasks. And then, of course, I could go into this again and say, like, okay, what do I need to have a power source, or where can I get a power source? But what I asked it is, where can I get the most reliable pneumatic components for this machine? And it actually gave me this answer. The second one, I cannot mention who it was. But the very first outcome was Festo as a leading manufacturer of pneumatic components. So yeah, that's some ideas of where we could get. Of course, I have to take it a step back to reality, where we at the moment. So Michael, I don't know if he's here. No, I didn't see him. I know he's in Barcelona. Hi, Michael. Michael Planck. He did some work on this together with Daniel Brauchle and very much abstracted the idea of, can we have a valve that is designed by a machine, right? That was the basic idea. And then we stepped away from moving parts for the start, and we just moved to this Tesla valve that is just having a geometry that you need to optimize. So it's not very generative, but in the end, they had a by a machine made optimized first valve that is now on the desk of Michael. Martin, sorry, not Michael, Martin Planck. And it's it's designed to have a certain throughput, right? A certain throughput in one direction and like blocking in the other direction. It's the first step. We are still having a long way to go. There is another work coming up from Tom Hofer. He will look at a cylinder. Maybe we can design a cylinder in a similar way. Let's see what comes out of it. But it is a very interesting direction. And as I said, this left part, I have a good feeling. On this right side, I don't know. I mean, there are some directions. There are some things that are interesting to look at, and I think we should look at it. I don't know if it will be solvable because it's a very complex task, but it might help, right? So there might be models that make our work easier, that make our work faster, and that's in the end already a very good thing. So what I want you to take away from this talk is, hopefully you saw that AI models or methods in the last few months, they developed really rapidly, and they still do. So they're still coming out new models basically every day that do more things. I didn't include it, but there is, instead of 2D images, there is already a model that makes text to 3D model, right? So I didn't include it in the talk, but it is there, so you can use it. You can have a 3D model out of text. many aspects of engineering can be supported by AI methodologies. And I think the main challenge is the understanding, right? How do things work together? How do physics work? This basic real world understanding of how something functions and how you simulate it. So I strongly encourage everyone to take a look back at symbolic AI, more rule-based AI for things where it shouldn't go wrong, right? So in general, it shouldn't go wrong. And that's it for my talk. Thank you very much. If you want to connect with me, you can scan this code or just find me around. I'll be here, and I'm happy to take questions.